Transmission Control Protocol, TCP, by Tucker Peterson. What is TCP? TCP is a standard that defines how to establish and maintain a network conversation through which application programs can exchange data. TCP works in unison with the Internet Protocol, or IP, which defines how computers send packets of data to each other. Together, TCP and IP are the basic rules defining the Internet. The Internet Engineering Task Force defines TCP in the Request for Comment Standards document number 793. The TCP/IP model. There are 4 layers to the model: application, transport, internet, and physical. The comparison of the models. On the left of the presentation there is the OSI model, which begins with the physical layer at the bottom. The physical layer transmits raw bit stream over the physical medium. The second layer, the data link layer, defines the format of data on the network. The third layer, the network layer, decides which physical path the data will take. On the transport layer, which is number 4, transmits data using transmission protocols including TCP and UDP. Session layer, number 5, maintains connections and is responsible for controlling ports and sessions. The presentation layer, number 6, ensures that data is in a usable format and is where data encryption occurs. The 7th layer, the application layer, is the human-computer interaction layer where applications can access the network services. On the right, we have the TCP model, which begins with the application, presentation, and session all combined into one layer, which is the application layer. It has the functions of the SMTP, FTP, DNS, and HTTP, and so on. The next layer is transport, which houses the SCTP, TCP, and UDP layers, or the protocols rather. The third layer is the network layer. That houses the DCMP, IGMP, RARP, and ARP protocols. And the final layer is the host-to-network or physical layer of the TCP model. How does it work? TCP is a connection-oriented protocol, which means a connection is established and maintained until the application programs at each end have finished exchanging messages. It determines how to break application data into packets that networks can deliver, send packets to and accepts packets from the network layer, manages flow control, and, because it is meant to provide error-free data transmission, handles retransmission of dropped or garbled packets, and acknowledges all packets that arrive. In the Open Systems Interconnection, OSI, communications model, TCP covers parts of layers 4, the transport layer, and parts of layer 5, the session layer. Requests come down to the server through the stack, and the information is then broken into packets of different types at each layer. The data moves from the application layer to the transport layer, where it is sorted into TCP segments. Then to the internet layer, where it becomes a datagram. Then to the network interface layer, where it breaks apart into bits and frames. Finally, the server responds and information travels up through the stack to arrive at the application layer as data. How does it work? Examples. An example of how TCP works is a web server sends an HTML file to a client. It uses HTTP, or Hypertext Transfer Protocol, to send it. The HTTP program layer requests that the TCP layer set up a connection to receive the incoming packets. The TCP stack then takes the packets and numbers them individually, sending them onto the IP layer to deliver to the receiver. The TCP program layer asks for any packets it did not receive based on the numbers it did receive. Then, the TCP layer assembles the packets and sends it to the application. Another real-world example would be a person sending a message on a puzzle through the mail. The message is then written down, and the puzzle is taken apart and numbered. Each piece can be taken through different routes and take a different amount of time to arrive to the destination, and it can arrive out of order. The TCP protocol can be thought of as the puzzle assembler. The connection is maintained before the puzzle is sent until every piece arrives. And that is very important to distinguish between TCP and UDP, because TCP ensures that each packet is received in its entirety, and UDP works in a sense that it can work without certain packets being delivered. Error detection. The TCP layer simply reorders the packets that it did not receive. This form of detection creates latency. Latency is created because the packets that it does not receive have to be reordered instead of moving on without them, like I just mentioned with UDP. This protocol lacks when it comes to fast speeds, so UDP is generally used instead for a need for low latency and less jitter, which an example of services that use UDP are voice over IP, streaming video, and gaming. They generally rely on UDP because they have a lower latency and have less jitter. UDP, like I mentioned earlier, simply ignores the packets that were not received and does not reorder them. The UDP datagram has less information in the header, so it has less information to process, therefore featuring a lower latency. What is TCP used for? This protocol is used to the secure transmission between server and client. It guarantees the integrity of data sent over the network because it continually resends and re-receives packets that were not completely full. It is used to transmit data from other higher level protocols that require all data to arrive. Examples of these include Secure Shell, or SSH, File Transfer Protocol, or FTP, and Telnet for peer-to-peer file sharing and logging into another user's computer to access a file. Another set of examples, Simple Mail Transfer Protocol, or SMTP, Post Office Protocol, POP, Internet Message Access Protocol, IMAP, and all of these are used for sending and receiving email. And there's also HTTP, which is used by TCP for web access. Why is TCP so important? TCP is important because it establishes the rules and standard procedures for the way information is communicated over the internet. It depicts a series of layers that represent the way data is handled and packaged by a series of protocols as it makes its way from client to server and vice versa. It is the foundation for the internet as it exists today. It ensures that data transmission is carried out uniformly regardless of the location, hardware, or software involved. It is highly flexible and scalable, meaning new protocols can be introduced to it and it will accommodate them. It is also non-proprietary, meaning no one person or company owns it, which means it cannot be moderated in the protocols that it can accommodate. The location in the TCP/IP stack. The TCP/IP stack is a model that represents how data is organized and exchanged over networks using the TCP/IP protocol. It depicts a series of layers that represent the way data is handled and packaged by a series of protocols as it makes its way from client to server and vice versa. Like the OSI model, the TCP/IP stack is a conceptual model for data exchange standards. Difference between the two models. The difference between the two models is the level of specificity. The OSI model is more abstract in the manner at which data is exchanged. The TCP/IP stack is more specific, being comprised of the dominant set of protocols. Therefore, the OSI is abstract and more functionally based, while the TCP/IP stack is concrete and protocol based. The OSI model has 7 layers and the TCP stack has 4. And that is the end of this slideshow presentation. Thank you.